Recall, we're trying to answer the question, what can we construct with a compass and a straight edge? And so today we're going to be looking at three problems the Greeks really wrestled with. Three questions that they tried to solve and couldn't, and now we'll have the tools to answer them. But let me remind you what we've done so far. We've said that some number alpha can be constructed by compass and straight edge and this is assuming you start off with some unit distance, you know. This is from starting off with some unit distance. So using your compass and straight edge, you can double that unit distance. You can construct like length 2. You can bisect it. You can construct length 1/2. We argued we can construct all the rational distances, right? And then we went on to say that you can construct alpha precisely when alpha can be obtained by addition, subtraction, multiplication, division, and square root. From either just one, but once you have one and you start allowing yourself to add and multiply and divide, you quickly get all of the rationals. And I'll remind you that these first 4 operations, these are just field operations. So these leave you inside whatever field you're in. So if you have rational numbers and you're just allowed to add, subtract, multiply, and divide them, you stick with rational numbers. And so it's really the square root that's expanding your field, right? So then last time we started thinking about, well, what happens as we expand the field? And so we say, okay, you could have some q, and then you expand q by constructing something like the square root of 2. We know how to do that. And so now you have everything you can get from q and the square root of 2. And then we saw that when you have q expanded by the square root of 2, things in here are of the form a, let's write it here, a plus b square root 2, where a and b are rational numbers. That is, this is just a degree 2 extension. If you look at the degree of q extended by the square root of 2 as a vector space over q, that degree comes out to be 2. And then we said, well, we can expand it again. You could expand this again by then saying, well, you know, I don't have like the square root of 3, so let's throw that in there as well. So q extended by the square root of 2 and the square root of 3. And now things in here, well, it is combinations of rationals and square roots of 2 and square roots of 3 and square roots of 2 times square roots of 3. But if you're thinking in terms of your coefficients belonging in the previous field, then this will be of the form just c plus d square root 3 if your c and your d are allowed to be coefficients in the previous field. And so we saw that again, this is just a degree 2 extension. The degree of q extended by root 2 extended by root 3 over q extended by just root 2 is just going to be 2. And you can continue in this way, saying, okay, let's just keep adding some other square root that's missing. You know, like what's missing now? Well, you don't have the square root of 5, and so maybe you want to add in the square root of 5 along with these other ones. And that again will be just a degree 2 extension. A degree, so this as a vector space over this is of dimension 2, so we call it a degree 2 extension. And it continues that way. And not only can you take like square roots of you know, integers, you know, you could also have included here something else like you don't have yet the square root of the square root of 2 plus the square root of 3. So that could have been the thing you added as well. You're just adding the square root of something that had been in the previous field but whose square root hadn't have been. Yeah?
So it's like the degree of this root 2 root 3 with the square root of root 3 the same as the degree as if you're expanding by root 2 root 3 over 5? Like, are they similar degrees when compared to the cube expanded by just root 2 root 3? So like expanding by the third term is the same no matter what that third term is?
Yeah, that's right. That's right. So in general, if this is just we'll call this like field 0, and then we'll call this, field 1, which is just whatever field 0 was extended by the square root of something inside of field 1. So here my x is some element that is inside of field 0. But the square root of x was not. The square root of x was not inside of field 0. That's why I need to include it to extend it. And each time you do that, no matter what you're extending by, then you have some field 2, which is just whatever field 1 was extended by the square root of something that was in field 1. I'll just call it y, where your y was something that was in field 1, but its square root of y was not inside of field 1. If you just keep extending it this way, each of these will be degree 2 extensions. Yeah? Okay. But we actually know something a little bit more. Last time, then you get some field 3 and so forth. We saw that if I want to know what is the degree of, say, field 3, over your original field, you can just multiply your degrees. You say, well, this was a degree 2 extension, and then you extend it by degree 2 again, and then you extend it by degree 2 again. So the degree of field 3 over field 0 would be just 2 to the n, 2 to the 3. 2 cubed. In general, the degree of f to the n over f0 will be just 2 to the n. Where each fk is obtained from the previous by extending by some square root of an element that was in the previous field, but whose square root was not in that field. I need the second condition, because if I extend by like square root of 4, I'm not adding anything, right? If I had put a square root of 4, it would still be the same field. It'd be, there wouldn't be, it would be a degree 1 extension. It would be the same field. Okay, so this follows from what we showed last time, that these degrees just multiply together. But let's think about what this tells us for constructibility. What does it mean for alpha to be constructible? Well, there's some way to build it up by doing your field operations and then adding sufficiently many square roots. But you should think each time you're introducing some square root symbol, you're just having to extend by something, right? So I don't know what alpha is going to be, but maybe it has quite a few square roots. But that just means it's sufficiently far down. Here, you've had to add so many square roots to get there. So really, this is equivalent to just saying that alpha is inside of some Fn, where Fn is how we define it over here, right? But let's think about what that means for alpha to be inside of some Fn. Like maybe our alpha is something like, a half plus the square root of 2 minus 3 square roots of the square root of 2 plus the square root of 3, right? Well, that alpha lives right in here. That alpha would be inside this F3. We can get to it in 3 steps. We need to add a square root of 2 and then a square root of 3, and we can get to this alpha. That alpha is inside of here. But notice something. Since alpha is an element of this field, if I just were to take Q and extend it by alpha, that would also have Q as a subfield. But moreover, that would be some subfield of this guy. That would be a subfield of Q extended by all of these pieces, root 2, root 3, and the square root of the square root of 2 plus the square root of 3. Right? Because anything I can give alpha, I would be able to get by doing all these pieces. But you can imagine there's probably stuff over here that's not in this field. Like you can play with it, and I don't know. Like, are you able to get a square root of 3 from this? Probably not if you're only doing rationals and this guy. Maybe, and you can play around and try it. Multiply them together to see if you can. So maybe Q sum by alpha is actually this whole field, but it's definitely at least a subfield of this field. But then that can cause us to think about, well, what is the degree? What is the degree of Q extended by alpha over Q? I have no idea. I don't know. But I know this degree down here. I know the degree of Q extended by the square root of 2 and the square root of 3 and the square root of the square root of 2 plus the square root of 3. We said that degree over Q comes out to be 8. Comes out to be 2 times 2 times 2. Came out to be 2 cubed, 8. So whatever this degree of Q extended by alpha is, well, it's something that when you times it by this other degree, it gives you 8. So whatever it is, it's some degree, whatever its degree is, it must divide 8. It divides 2 cubed. Is that clear? It could be 4, it could be 2, it could be 8. I don't know what it is, but it divides 2 cubed. And in general, we can say this. Since alpha has to live inside of Fn, that means that you're going to have this construction where Q is a subfield of Q extended by alpha is a subfield of Fn, because Q is a subfield of Fn and alpha is inside of Fn. And so that's going to give you, so that implies that the degree of Q extended by alpha over Q must divide the degree of Fn over Q. The degree of Fn over Q is 2 to the n. So this must divide 2 to the n. So it must itself be 2 to some power. 2 to the k for some k greater than or equal to 0. It could be 1, it could be 2, it could be 4. Whatever it is, the degree of Q extended by alpha over Q is 2 to the k. And this is the main result. That for alpha constructible, the degree of Q extended by alpha over Q is some power of 2. And that result will let us do some really cool things. So let's do them. We're going to use that result to answer 3 problems the Greeks could not. There are 3 classic construction problems that naturally come up, but the Greeks were unable to answer. They didn't have this algebraic machinery. The first one is the problem of doubling the cube. So this is kind of a strange problem because a cube is a 3-dimensional object, but you can imagine a cube sitting on a plane, or you might even just imagine like the projection of a cube onto a plane, but we'll just imagine the cube as sitting on your plane. And the question is, can we construct another cube using compass and straight edge? That is, can we construct the side length of this other cube so that the volume of the second cube is twice the volume of the first cube? You know, can we double the volume of a cube? Can we, so given a cube, can we construct another cube with twice the volume? So let's think about this. I mean, so I'll try to draw it. It's going to be a little bit bigger. So something like this. Okay, well, it was given some cube. We don't have, you know, we don't have a ruler, so we can't measure the length of the side. So we'll just say its side length is 1. And so the volume of this first cube is just 1, right? So I need to get the volume of my second cube to just be 2. So what does my side length need to be? Yeah, the cube root of 2. I would need the side times the side times the side. I need side cube to be 2. So my side here has to be the cube root of 2. And so what this problem is actually asking is just, can you construct the cube root of 2? Given a unit length and compass and straight edge, can you construct the cube root of 2? Well, let's think about the cube root of 2. What is the degree of q extended by the cube root of 2 over q? What kinds of creatures live inside of q extended by the cube root of 2? If x is in q extended by the cube root of 2, what form does x have? Yeah, so you could say it's some a plus, so here my a and my b are going to be rational numbers. A plus b cube root of 2. Is that it? Well, what happens when you do cube root of 2 times cube root of 2? Yeah, you also have a cube root of 4 piece. So you need to take a second and convince yourself that this basis, so like 1, cube root of 2, and cube root of 4 are linearly independent over the rationals. Well, clearly the cube root of 2 is independent from 1 because cube root of 2 is irrational. You can prove that. So then you just need to prove that the cube root of 4 isn't secretly something of the form a plus b cube root of 2. But you can prove they can cube both sides and show it gives you a contradiction. And so these really are 3 linearly independent pieces. And then you just want to argue that this is really giving you a basis. That in q extended by cube root of 2, you have as a basis over the rationals 1 cube root of 2 cube root of 4. But you can do that. You can just check that things of this form are closed under the field operations. So if you take 2 things of this form, you add them together, it's still of this form. You multiply them together. You got to do a little bit of algebra, but it's still of this form. Okay, maybe the hardest one is to think that these have multiplicative inverses. So do like 1 over this, and then you have to like rationalize the bottom, right? But we've done this kind of work before, and you can do it again. I think this is pretty highly believable that yeah, it really does come out to be this is your basis. And so you just get then that this degree is 3. But 3 is not of the form 2 to some power. And alpha is only constructible if the degree of q extended by alpha over q is 2 to some power. And so hence it follows that the cube root of 2 cannot be constructed, is not constructible.
Does that fall for any cube root? Or like some prime number?
Well, you have to make sure that it's a cube root that's like actually a cube root, right? That isn't like cube root of 8, wouldn't work because that just simplifies to 2. But outside of that, yeah, you can verify in general, like if this is a prime, or even if it's just something that you're left with some like cube root of a prime piece, you end up with it. So you should do this proof. This is like a good homework to verify that these are linearly independent. If it was like cube root of 15 or whatever, sure enough. Okay. So hopefully this is beginning to show like this is a really powerful criteria for constructibility. It lets us solve this problem of the Greeks. Let's talk about one more problem of the Greeks. So this is one that's like made it into everyday language, squaring the circle. So like maybe you've heard this idiom of like they're trying to square the circle, which means like you're trying to do an impossible problem. Because it turns out this is impossible. The Greeks had asked, if you're given a circle, can you construct a square such that the square has the same area as the circle? Okay, that probably wasn't the best square. It looks a little bit too small, but something like this. So given a circle, where you want to construct a square with the same area. Okay, so you're given some circle. I don't know what this distance is. We could just say the radius is unit distance 1, although it's fine if it's something else as well. So the area of this circle is just pi r squared, it's just pi. And so you're given a circle, has area pi. You want to construct a square with area pi, so you need the side length to be the square root of pi. So can we construct the square root of pi becomes the question. Well, if we could construct the square root of pi, then we could construct pi. Because you can just multiply by itself, you can cover pi. And if you can construct pi, you can also construct square roots of those things, so you can construct the square root of pi. So really the question is just, can you construct pi? Or equivalently, the square root of pi. So what, you'd help me out. Can you? Can we construct pi? Something of length pi? Yeah.
Actually, if we take pi to be, if we assume that pi is irrational, could we then consider square root of pi and pi as separate bases, and like vectors for the space, and then we get the degree is 3. Can we do it that way if we assume that pi is irrational?
So I think this is a little confused. So you want to say something like q extended, let's just think about q extended by pi. And then you want to say, okay, I know pi is irrational. And so then how are you using this?
Then,
what is that basis for this space?
So we know that
pi is independent from 1 over the rationals, okay?
the square root of pi is also independent over the rationals. You can't multiply pi by.
Yeah, I just want to do it by pi right now. Let's forget about square root of pi. You can do a similar argument.
Okay. But
what else would have to be in this basis? Is it enough to just have 1 and pi? Or are things in here just of the form a plus b pi? Sorry, what was that?
You need 1 over pi for the inverse, but that you need that in the basis also.
Okay, great. We need like a 1 over pi. You might wonder like, how do you get 1 over pi? But let's just ask something more fundamental. How do I get pi squared? Okay, can pi squared be written of this form? Can it? Can you write pi squared as some a plus b pi, where my a and my b are rational numbers? Can you? If you could write pi squared as some a plus b pi, then that would mean that pi is a solution to, pi would become a solution to, or a root of, the function x squared minus bx minus a, right? Where your a and your b are rational. Is pi a root of this guy? Why not? No, you can have irrationals that are roots of quadratics. It's not because pi is irrational. Is pi the root of some polynomial with rational coefficients? Ah! In 1882, Lindemann showed that pi is transcendental. That is to say, pi is not algebraic. That is to say, pi is not a root of any polynomial with rational coefficients. What that implies is you can't write pi squared in terms of just, some a plus bi. But it also means you can't write pi cubed as some a plus b plus c pi squared, right? Because if you could, then you would get that pi is a root of some cubic, pi cubed minus, x cubed minus cx squared minus bx minus a. So you can't write pi cubed as some linear combination of the previous terms either. So you need pi cubed. And you also, same thing, you can't write pi to the fourth as some linear combination of the previous terms. Else pi would be the root of some degree 4 polynomial. And so since pi is not the root of any polynomial with rational coefficients, you need to include all of the powers of pi in your basis. But if you have to include all the powers of pi in your basis, then what does that mean for the degree of q extended by pi over q? It's infinite. It's infinite. In general, whenever you include some transcendental number here, it could be e. In 1880, they also showed in 1880s, it's a similar result that gives you both of these. It's powers of e. Is transcendental. And so you have a q extended by e over q is infinite. So e is not constructible. Since it's infinite, it's not just a power of 2, it's infinite. And so this implies that pi, or in fact any transcendental number, is not constructible. Cool? Okay. The last one I want to talk about, we'll spend a few more minutes on. And maybe this is the most surprising of them. Now, one of the very first things Euclid does in the Elements is it shows us how to bisect an angle with compass and straight edge, right? You have some angle. You can just throw your compass down, get 2 points that are then both equidistant from the vertex of your angle, and then from here, you can copy some distances. And then if you construct the ray that goes through these points using a straight edge, Euclid shows you've bisected your angle. It's one of the very first things he does. So you can imagine how much it irritated him that he couldn't find a way to trisect the angle. You can trisect a line segment. You had a homework problem, like an exam problem on this. If you have a line segment, you can break it into 3 equal pieces. So there was a way to trisect the line segment. But can you trisect an angle? Well, how are we going to get our hands on this? So the problem is given an angle. Given an angle. Well, you trisect it. You want to partition into 3 equal angles. Well, you might think there are some angles you can trisect. If I gave you a right angle, you would be trying to figure out what is a 30-degree angle, right? And you can construct 30-degree angles. So let's think back. Why can we construct a 30-degree angle? Well, a 30-degree angle is constructible. That's equivalent to saying that you can construct sine of 30 degrees and cosine of 30 degrees. Because given something of length 1, you just need to be able to determine the x and y coordinates. And then you know that sine of 30 degrees is just at a half, and cosine of 30 degrees is out at √3/2. And since these are numbers that we can get from addition, multiplication, subtraction, division, and square rooting of the rationals, these are constructible. So you can construct 30 degrees. So the problem's not asking like, is there any angle you can construct, but we're saying, in general, can you construct a given angle? And so to prove you can't do it in general, I just need to give you one example of an angle you can't construct, you can't trisect. So my claim is you can't trisect a 60-degree angle. So to show that, I'm going to show that 20 degrees is not constructible. Well, if 20 degrees were constructible, that would tell you that cosine of 20 degrees is constructible. And if you can make cosine of 20 degrees, you can also make sine of 20 degrees, because sine and cosine are related by quadratic. And so really showing that 20 degrees is not constructible is equivalent to showing that cosine of 20 degrees is not constructible. So this is what I'm going to prove. That there are some angles you can't construct. And so since we can construct a 60-degree angle, you can't trisect a general angle, or else you would have a contradiction. Okay. How can we prove this? Well, I'm going to reach into your memory of trigonometry and see if you remember your triple angle formula. So maybe you never even learned this, but you learned like how to, like what is cosine of alpha plus beta? And so you had like the formulas for the sum of angles. And so you can recover the double angle formula in the same way you can recover a triple angle formula. Your triple angle formula just says that cosine of 3 theta is, well, there's a few different forms, but whenever you have a cosine squared, you can change to 1 minus sine squared or vice versa. And so you can show that this comes out to be something equivalent to 4 cosine cubed of theta minus 3 cosine of theta. So let's let our theta be 20 degrees, and then I'll just denote cosine of theta, or cosine of 20 degrees, I'm just going to denote that by x. So let's see what we get. Here we get cosine of 3 theta, which is cosine of 60 degrees, which is up here, so this is 1/2. That's exactly why 60 degrees is constructible, because cosine of 60 degrees is just 1/2, which is a constructible number. Then here I have 4 times cosine cubed of 20 degrees, so that's 4x cubed, minus 3x. And so cosine of 20 degrees is a root of the expression 4x cubed minus 3x minus 1/2. Right? If you were to plug in x equals cosine of 20 degrees into here, you would get 0. I don't want to have to deal with a half, so I'm still going to think about cosine of 20 degrees as being a root of 8x cubed minus 6x minus 1. Because if you plug it into there, you still get 0. I just multiplied by 2. And so the question I want to ask is, what does q extended by x, extended by this cosine of 20 degrees, what does it look like? What do elements in here look like? So what is a basis for q extended by cosine of 20 degrees over the rationals? Okay. Here I'm just going to, for shorthand, I'm just going to stick with calling this x, q extended by our x. But x is not a variable, it's a particular quantity, cosine of 20 degrees. So what is that basis? Well, there's one thing I don't need in my basis. I don't need an x cubed. Right? So you might think you might need a 1, you might need an x, you might need an x squared, but you definitely don't need an x cubed, because there's a solution. You could solve for x cubed. My x cubed is just secretly, well, 8x cubed is just 6x plus 1. So my x cubed can be written in terms of these other elements. It's just 6 divided by 8, x plus 1/8. So I don't need an x cubed. And similarly, I don't need anything bigger than x cubed. I don't need an x to the 4th, because I could just multiply this all through by x. And x to the 4th is in terms of smaller guys also. So once I've solved for 1 power in terms of the smaller ones, I know I don't need any more powers. So I need at least a 1. Well, I might need a 1 in x and x squared, but I definitely don't need an x cubed. What I want to show is I want to convince you that 1x and x squared are actually linearly independent. So by this argument, these are enough to span to give you everything. But you might think, well, maybe the x squared is also redundant. Right? That should be a concern. So let's think about that. Are we able to solve for x squared in terms of the smaller ones? So what we really want to know is, like, do you really also need that x squared there? You know, can you solve, you know, can you know, write x squared as some a plus bx? Well, you know, it's kind of weird. It's like we don't even know what x is. All we know is x is a root to this guy. It's a solution to this. So I have this polynomial, 8x cubed minus 6x minus 1. And so what we should really do is be thinking about this polynomial. If I do have some solution of this form, then that's saying that x is also actually a root of some quadratic. Which is saying that when you have this cubic, you actually could have factored it. The question is, can you factor it? If you can factor this into some quadratic in a linear piece, so something, you know, some x squared plus some x plus c, and some x plus you know, some other rational term. If you can factor this, then from this being 0, you get that one of these are 0. And that would tell you that you also have a way to write x squared in terms of smaller things, or even x itself as just a rational value, right? So the question just becomes, can you factor it? If you can factor this expression over the rationals, then x squared is also redundant. If you can't factor it, then you really need your 1, your x, and your x squared. Is that clear? Okay, great. But if we can factor this, since this is a cubic, one of the terms must be linear. And a term being linear is saying that x is actually a root of this guy, and so that's giving you that your x is actually a rational value. So this being linearly independent comes out to be equivalent to saying, is there a rational root to 8x cubed minus 6x minus 1? Does this function have some rational root? And so what I'm going to argue now is that this function does not have a rational root. And since it doesn't have a rational root, there's no way to factor this down. And since there's no way to factor that down, x cubed is the smallest thing you can simplify. And so you have to have 1x and x squared in your basis. That is, this is a degree 3 extension. Okay, so does this have a rational root? We're going to need some space for this, so let's come over here. My polynomial is 8x cubed minus 6x minus 1. So suppose you do have some rational root of 8x cubed minus 6x. Is it minus 1? Minus 1. So let's call that root something. Let's say that root is just, let's say p over q, where we can insist that our p and our q have been simplified, right? So we can insist that they're relatively prime, where the greatest common divisor of p and q is 1. This is going to begin looking familiar for those who have done like the B55, right? Okay, so what does this mean? Well, let's plug it in. That means 8 p cubed over q cubed minus 6 p over q minus 1 is 0. But that implies, multiplying through by q cubed, 8 p cubed minus 6 p q squared minus q cubed is 0. Let's think about this relationship. 2 divides the first term, and 2 divides the second term, because this is a multiple of 2 and this is a multiple of 2. Hence, that tells you 2 must divide the last term. You can just move the q cubed over, and you get q cubed as some even expression. And so q cubed is even. But the only way for q cubed to be even is if q is even. So that means 2 actually divides q. That is, we could write q as 2 times some k, where here my p, my q, and my k are all integers. P, q, and k are all integers. Let's plug that back in. Replace this with a 2k, so I have 8p cubed minus, I'm plugging in 2k for my q, so it's going to be 4k squared, so it becomes minus 24pk squared. Plugging in 2k here becomes minus 8k cubed is 0. Each of these terms has an 8, so you can pull that out, divide by 8. The other side's 0, so it just becomes p cubed minus 3pk squared minus k cubed is 0. Yeah? I think this looks good. But what does this say? Notice p divides the first term, and p divides the second term. So if I were to move this to the other side, I would have k cubed as a multiple of p. But since your p and your q are relative, have no common factors, well, that also means that p and k have no common factors. So something's kind of weird has happened here. We just saw that k cubed is some multiple of p, that p divides k cubed. You can also show that since k divides both of these terms, k must divide p cubed. So how can it be that p and k have no common factors, but p divides k cubed and k divides p cubed? Well, the only possibility is that your p and your k are plus or minus 1. You know, the only common factor they can have is 1. This is saying they have common factors, but the only common factor they're allowed to have is 1. So it must be plus or minus 1. But then you can go in, you can try plug in various combinations. You know, you can try and plug in 1 for your p, or plus or minus 1 for your k, and it's not a solution. So that gives you a contradiction. These solutions don't work. The only possible solutions are not solutions to this. You know, plug in 1, you get 1 minus 3 minus 1. That's not 0. Plug in minus 1, still doesn't work. Okay. So you can't factor this guy over the rationals. He can't factor. He has no rational roots. Which means this basis has 3 elements in it. Which means the degree of q extended by cosine of 20 over q is degree 3. Which means cosine of 20 degrees is not constructible. Which means that 20 degrees is not constructible. But 20 is a third of 60 degrees, which is constructible. So you can construct a 60-degree angle, but there must be no way to trisect it, because we can't get to 20 degrees. And hence we can't trisect an arbitrary angle. Okay, we'll stop there.